Subscripts. Classes, structures, and enumerations can define subscripts, which are shortcuts for accessing the member elements of a collection, list, or sequence. You can use subscripts to set and retrieve values by index without needing separate methods for setting and retrieval. For example, you can access elements in an array instance as some array index and elements in a dictionary instance as some dictionary key. You can define multiple subscripts for a single type, and the appropriate subscript overload to use is selected based on the type of index value you pass to the subscript. Subscripts are not limited to a single dimension, and you can define subscripts with multiple input parameters to suit your custom type's needs. Subscript syntax. Subscripts enable you to query instances of a type by writing one or more values in square brackets after the instance name. Their syntax is similar to both instance method syntax and computed property syntax. You write subscript definitions with the subscript keyboard and they specify one or more input parameters and return type in the same way as instance methods. Unlike instance methods, subscripts can be read, write, or read only. The behavior is communicated by a getter setter in the same way as for computed properties. Subscript index:int goes to int, get, and set. So set takes the new value, get has it, and the type of the new value is the same as the return value of the subscript. As with computed properties, you can choose not to specify the setter's new value parameter. A default parameter called new value is provided to your setter if you do not provide one yourself. As with the read-only computed properties, you can simplify the declaration of a read-only subscript by removing the get keyword and its braces. Subscript index:int goes to int and return an appropriate subscript value here. Here is an example of a read-only subscript implementation which defines a times table structure to represent an n times table of integer struct. Times table let multiplier :int, subscript index:"int goes to int, return multiplier times index. Let 3 times table equal times table multiplier :3. Print 6 times 3 is 3 times table of 6. In this example, a new instance of times table is created to represent the 3 times table. This is indicated by passing a value of 3 to the structure's initializer as the value to use for the instance multiplier. You can query the 3 times table instance by calling its subscript as shown in the call to 3 times table of 6. This requests the 6th entry in the 3 times table, which returns a value of 18, or 3 times 6. Note, an n times table is based on a fixed mathematical rule. It's not appropriate to set 3 times table some index to a new value, and so the subscript of times table is defined as a read-only subscript. So as you can see, there is just a return multiplier times index in the subscript. There's no getter or setter. Now, subscript usage. The exact meaning of subscript depends on the context in which it is used. Subscripts are typically used as a shortcut for accessing the member elements in a collection, list, or sequence. You are free to implement subscripts in the most appropriate way for your particular class or structure's functionality. For example, Swift's dictionary type implements a subscript to set and retrieve the values stored in a dictionary instance. You can set a value in a dictionary by providing a key of the dictionary's key type within subscript brackets and assigning a value of the dictionary's value type to the subscript. Var number of legs, spider has 8, ant has 6, cat has 4. Number of legs, bird equals 2. For example, above defines a variable called number of legs and initializes it with a dictionary literal containing 3 key value pairs. The type of the number of legs dictionary is inferred to be string going to an int. After creating the dictionary, this example uses subscript assignment to add a string key of bird and an int value of 2 to the dictionary. For more example information about dictionary subscripting, see accessing and modifying a dictionary. Swift's dictionary type implements this key value subscripting as a subscript that takes and returns an optional type. For the number of legs dictionary above, the key value subscript takes and returns a value of type int, question mark, or optional int. The dictionary type uses an optional subscript type to model the fact that every key will have a value, and to give a way to delete a value for a key by assigning a nil value for that key. Subscript options can take any number of input parameters, and these input parameters can be of any type. Subscripts can also return any type. Subscripts can use variadic parameters, but they can't use in-out parameters or provide default parameter values. A class or structure can provide as many subscript implementations as it needs, and the appropriate subscript to be used will be inferred based on the types of the values or values that are contained within the subscript brackets at the point at which subscript is being used. This definition of multiple subscripts is known as subscript overloading. While it's most common for subscript to take a single parameter, you can also define a subscript with multiple parameters if it's appropriate for your type. The following example defines a matrix structure which represents a two-dimensional matrix of double values. The matrix structure subscript takes two integer parameters: struct matrix let rows colon int columns colon int vargrid colon array of doubles init rows takes rows and columns int self.rows equals rows self.columns equal columns grid equals array repeating colon 0.0 count colon rows times columns, and the func index is valid row colon int column int goes to the boolean return the row greater than or 0 and row less than rows and greater than or equal to 0 and column is less than columns. If that's the case, the index is valid. Subscript is defined as a row colon int column int goes to a double get assert index is valid row colon row column. If not, we say index out of range. Otherwise, we return the grid subscript row times columns plus column. And if we want to set, then we will assert that the index is valid and then get the grid at row times columns plus column and set that equal to the new value. Okay, and matrix provides an initializer that takes two parameters, rows and columns, and creates an array that is large enough to store rows and times columns values of type double. Each position in the matrix is given an initial value of 0.0 to achieve this. The array size and an initial cell value of 0.0 are passed to an array initializer that creates and initializes a new array of the correct size. The initializer is described in more detail in creating an array with a default value. You can construct a new matrix instance by passing an appropriate row and column count to its initializer bar matrix. Matrix rows 2 columns 2. The preceding example creates a new matrix instance with 2 rows and 2 columns. The grid array for this matrix instance is effectively a flattened version of the matrix as read from top left to bottom right 0 0 0 0 0 0 0 0, and we are basically reading from top left to bottom right this matrix 2 by 2 matrix of zeros. Values in the matrix can then be set by passing row column values into the subscript separated by comma. So matrix of 0, 1 is 1.5, matrix of 1, 0 is 3.2, and that creates this following 2 by 2 matrix. The matrix subscript getter and setter both contain an assertion to check whether the subscript row and column values are valid, and otherwise will throw the indexes out of range errors. And the index is valid function is repeated here. An assertion is triggered if you try to access a subscript out of bounds, and so let some value equal matrix 2, 2, and this triggers the assert because 2, 2 is outside the matrix bounds. And that's it for subscripts.